When modeling the complex physical dynamics of a multiple subsystem network, engineers generate endless pages of time-domain differential equations. By the time you link the actuator to the plant and the plant to the sensor, you face a dense, interwoven wall of calculus. This creates an immediate cognitive bottleneck. The massive mathematical density exhausts human working memory, and the intuition you need to actually understand how the system behaves gets lost in the algebra. To survive the analysis of highly complex systems, engineers transition away from algebraic calculation and toward visual, structural reasoning. The goal of this structural approach is specific. Take a labyrinth of interconnected physical subsystems and collapse them all down into a single, highly readable equivalent input-output transfer function. We do this using the block diagram. This graphical tool maps exactly how signals route through various physical components. This graphic shows the 4 atomic units of these maps: the input and output signals themselves, the transfer function of a specific system block, a summing junction where multiple signals are combined, and a pickoff point distributing an undiminished signal to new pathways. By treating pure math as a physical, spatial topology, you rebuild the structural intuition required to design real controllers. No matter how large a control architecture grows, its internal blocks connect in one of 3 fundamental ways. The first and simplest is the cascade, or series form. Looking at this diagram, we see 3 separate subsystems linked sequentially. To find their equivalent transfer function, you simply multiply their individual equations together to form one unified block. This multiplication relies entirely on one physical assumption: the connected systems do not load the adjacent systems. If a downstream component draws energy from the one before it, the physical output changes, and direct multiplication no longer applies. The second common arrangement is the parallel form. Here, the input signal splits at a pickoff point and enters multiple subsystems at the exact same time. Because they operate simultaneously, their outputs are algebraically summed at the end to create the overall equivalent transfer function. The third arrangement is the feedback, or closed-loop form. Panel B illustrates this architecture. A portion of the system's output signal is routed backward and evaluated against the input. This difference generates an error signal, driving the main system forward. The equivalent transfer function collapses to a specific mathematical fraction, the forward gain, g, divided by 1 plus or minus g times h. The product of g and h in the denominator is critical. Engineers define this as the open-loop transfer function. Every massive control system you encounter is ultimately built by stacking these 3 structural components: cascade, parallel, and feedback. In reality, complex control loops overlap. To collapse a sprawling network into our 3 basic topologies, we have to physically move the blocks around the diagram. The standard strategy is to identify the innermost nested loops, collapse them, and work progressively outward toward the main system boundaries. This diagram demonstrates the rule for moving a system block past a summing junction. Look at panel A. When we shift the main block g of s to the right, we change the mathematical reality of the secondary branch. To maintain exact algebraic equivalence, we must artificially inject that same g of s transfer function into the adjacent branch. Depending on the direction you move the block, you will multiply the neighboring branch by either g of s or 1 over g of s. An inverse set of scaling rules applies when moving a block past a pickoff point. In panel A, moving g of s to the right requires placing a 1 over g of s block into every newly exposed parallel branch. These shifting rules exist strictly to guarantee that the final physical signal remains entirely undisturbed from the perspective of the overall system output. But there is a glaring inefficiency in this process. Manually pushing blocks branch by branch is highly heuristic. If you scale a single pickoff point incorrectly, that error cascades through the rest of your reduction. Block diagrams are excellent for building an initial intuition, but when applied to deep, overlapping architectures, manual block shifting becomes a liability. We need a more precise, automated tool. That tool is the signal flow graph, a minimalist framework built specifically to solve complex reduction algorithms without the visual clutter. This graphic breaks down the translation. On the left, bulky system boxes are replaced entirely by simple directional lines, or branches. On the right, the physical signals, the inputs, the outputs, and the summing junctions, all collapse into tiny individual nodes. The actual transfer functions don't disappear. They are instead treated as mathematical weights applied directly to the directional branches connecting the nodes. The exact topological relationship of the block diagram survives, but the interface is stripped down to pure signal routing. By converting the system into this lightweight architecture, engineers can abandon error-prone block shifting entirely. They solve the entire network simultaneously with a single equation. That equation is Mason's rule. It's an algorithmic formula that reads a signal flow graph and computes the overall equivalent transfer function in one pass. This chart displays a multi-loop signal flow graph. Attempting to reduce this manually would require dozens of individual block shifts. Mason's rule handles it by breaking the map into 3 strict components. The first component is the forward path gain, T sub k. This is the product of all branch gains found by tracing a path straight from the input node R of S to the output node C of S. For example, multiplying the entire central line from G1 through G7. The second component evaluates the closed circuits, known as loop gains. A loop gain is calculated by tracing a path that starts and ends on the exact same node, like the circuit connecting G2 and H1. A valid loop cannot pass through any node more than once. The final element deals with non-touching loop gains. We scan the graph for distinct loops that do not share a single common node. The loop formed by G2 and H1, for example, is entirely isolated from the loop formed by G4 and H2. These isolated loops form the basis for delta, the determinant symbol in Mason's formula. Delta follows an alternating algebraic pattern: 1 minus the sum of individual loop gains, plus products of non-touching loops taken 2 at a time, minus products taken 3 at a time. Finally, the delta k term tailors that determinant to each specific forward path. Calculate delta k by looking at your master delta and eliminating any loop gains that physically touch your current forward path. Despite looking like an abstract wall of variables, Mason's rule automatically encodes every physical path and isolated dynamic into one equivalent calculation. Whether you rely on the physical manipulation of block diagrams or the algorithmic execution of signal flow graphs, the engineering objective is identical. You are distilling a chaotic labyrinth of mechanical and electrical components down into one clean equivalent transfer function. We bypassed the limits of raw time-domain algebra by turning a math problem into a spatial routing map. Structural intuition prevents mathematical fatigue from obscuring the physical system under design. Without it, engineers lose sight of the hardware itself. With a unified single transfer function finally established, the system is now fully prepared for formal stability analysis. Mastering the reduction of multiple subsystems provides the indispensable connection between theoretical modeling and the design of real-world controllers.